Okay, so welcome to the 11th video in the Discrete Structures series, and we're going to start this video off with a new chapter from our syllabus, and it's integers and matrices. And in this particular video, we'll be looking into the concepts of divisibility. We'll look into the common notations used in divisibility, and then we'll follow up with a couple of theorems. The first one we're going to look at is called the division algorithm. And it's not actually an algorithm. The algorithm is just a traditional name given to this theorem. It's actually a theorem. And then we'll look into three specific theorems on the properties of divisibility. And these are pretty basic theorems, nothing too fancy here. The first thing that we're going to see is going to be the divides notation. And to put some more light into this topic, let us first have a look at the difference between the word division and divisibility. So division is a process, divisibility is a test. And when we are testing for divisibility, it only makes sense to do that in the sense of whole numbers. Because you see, division is always possible. If I take a division like 7 by 3, I could always calculate it in a fraction and get a result. But in order to say that 3 divides 7, I want the division to be exact. Okay, so the division between 7 and 3 is possible, but in terms of divisibility, 3 does not divide 7. Okay, it leaves some remainder. And that's the context for our divides notation. We say that A divides B if multiplying A with something will result to B, right? So basically A divides B means A times some K equals B, right? And K would be any integer. And that is also the formal definition of divisibility. We say that A divides B if A times some constant K is equals to B. And of course, an alternative way to mention the same thing would be B by A is an integer. Okay? And there is this symbol, does not divide. So if I put the divide sign and cross it this way, it is does not divide. So it would be true to say that 8 divides 40, but 8 does not divide 42. Okay? So just a matter of notation. We'll look into a couple of problems where this becomes relevant later. But yeah, these are just notations. The next thing that we're going to look at is going to be the division algorithm. So let me note that down. And as I mentioned earlier, this is not actually an algorithm but a theorem. I'm personally referring to this notation from Kenneth and Rosen, Discrete Mathematics. And in the textbook, he mentions that the word algorithm has been in use before him, right? So he also borrows it from traditional usage. Okay, that's enough trivia. Let's get into what this actually means. And I think the best way to understand this would just be to define it formally and then have a look at it with an example. So let me do that. It starts by assuming two variables. So let's say A is any integer and D is a natural number. We'll look into why these assumptions are made shortly, but for now let's play along. And then the theorem says that there exists two integers Q and R such that two things are true. So one thing is 0 less than or equal to R less than D. And another A equals D times Q plus R. Okay, so it's such that this is true. This looks kind of technical, but it really is not. I just want you to consider these by what they mean. D is divisor, Q is quotient, R is remainder, and A is the number that I'm trying to divide. Okay, and all of this should make perfect sense. And to justify that further, let's say I want to consider this quotient, 25 divided by 8. So first, intuitively, I know that 8 times 3 is 24, so my quotient is going to be 3, and my remainder is just going to be 1, okay, because 8 times 3 is 24, and adding 1 gives me 25. And now, in this context, let's try to make sense of the above definition. So I think it's easy to work backwards. I want to express this first. What I'm doing here is writing 25 equals the divisor 8 times 3 plus 1, okay? So I'm just writing this. And we'll trace this backwards to make sense of all of the remaining things. But the idea here is I want to choose the biggest number that I can multiply this 8 with so that it leaves a remainder between 0 and 8, right? Whatever I'm dividing with. And that should give you a clue about this one. So this basically mentions that my remainder has to be less than D, right? Because when I'm dividing 25 by 8, 9 cannot be a remainder, for example. So this part should also be clear. Whatever remainder I'm getting out of my division should be between 0 and D. Okay, this should make sense. Now this part should also be fairly simple because the quotient and the remainder that I want should also be integers. Otherwise, it doesn't really make sense to do the division. And we saw that in the earlier segment of the video. And that leaves me with these two assumptions. And remember, A is the number being divided here. right? I don't want to put any restriction in A if I don't have to. And therefore, it's fair to call A in the set of integers. But when it comes to the divisor, okay, let's break it down. What happens if the divisor is 0? I think this should at least be omitted safely because I don't want to really divide by 0. And that leaves me with the only question, why can't D be negative? I'm forcing it to be a natural number. I'm forcing it to lie in the domain of 1, 2, 3, 4 and so on. I'm not allowing it to be negative, right? So why is that? Because if you look at here again, I want my remainder to be between 0 and D. So a positive remainder cannot be more than 0 and less than some negative number, right? So D has to be positive. And since D cannot be 0, it cannot be negative, the only choices that remain for D is the set of natural numbers, right? So that's why we're limiting D to the set of natural numbers, because that is most consistent with the properties of division. So if I read this in plain English, take any number, divide it with any natural number, you're going to get some quotient and some remainder. That can be guaranteed, right? And the quotient and remainder are going to be integers. Next, we have a look at 3 particular theorems that discuss the properties of divisibility. And these are pretty basic theorem. The first theorem, and it states that if A divides B and A divides C, then A would divide the sum of B and C. And this is pretty easy to see. So for example, 8 divides 24, 8 divides 16, and therefore 8 would divide the sum of 24 and 16. But how do I prove this formally? I can borrow the definition of divisibility from earlier. So A divides B would imply A times some constant K is equal to B. Okay, and A divides C would similarly mean that A times some constant K2 would be equal to C. So I could add these equations together, and that would give me A times K1 plus K2 would give me B plus C, right? And since A times some constant is equals to this value, I could use the same logic, right? Because if this implies this, the reverse implication is also true in this case. So I could write A divides B plus C. And how many times does A divide B plus C? That's K1 plus K2 times. Okay. So 8 divides 24 3 times. 8 divides 16 2 times. So 8 divides 40 3 plus 2, that is 5 times. So this is what the first theorem suggests. Next, have a look at our second theorem. The second theorem also demonstrates a very basic concept. A divides B should imply A divides B times any constant C. Okay, so this is also pretty easy to prove. And for the same example, if 8 divides 16, 8 also divides any multiple of 16, right? It doesn't matter what I multiply 16 with, 8 would still divide it. And of course, this is only true for all C belongs to Z. Because if I start multiplying this with, let's say, a 1 by 10, then the result would not be divisible by 8. So what I multiply it with must be an integer. Okay, so how to prove this? So quite similarly, as a matter of fact, so A divides B would implies A times some constant K would be equal to B. And then I could multiply this equation with a C, right? Because I only want to get a group of BC in one side. So I could say A times K times C equals B times C. And since C is an integer, K times C is another constant, right? So I can see A times something is equal to BC. And this gives me the implication A divides BC. So also pretty basic. Let's have a look at the third one. And that describes the transitivity property. It says that if A divides B and if B divides C, you could say in chain, you know. So A also divides C. So this is an implication. And this is the transitive property. So to prove this, let's begin with this one. A divides B would implies A times some constant K would be equal to B. And the second fact that's given to me, B divides C, and this would imply B times some constant K would be equal to C. And let me distinguish these constants, call this 1 and call this 2. And all I want to do now is to get a relationship between A and C. So find a way to get B out, and there could be 100 ways to do that, but I'm simply going to multiply these equations. So I'm going to say A, B, K1, K2, okay? And it's going to be equal to BC. And then that would allow me to write A times K1, K2. And K1, K2, the product of two constants is also a constant, and this would be equal to C, right? And from this, I could conclude that A divides C. Okay, so pretty basic theorems, and this proof should also be very obvious. Okay, so before ending the video, let's have a look at one more question. So let me put the problem here. It says, let N and D be positive integers. And it asks how many integers that do not exceed N are divisible by D. So again, I think an example would help here as well. I'm dividing by d, so I would have take my number n to be something like 10, the bigger number, and the number that I'm dividing something like 3, right? So it's basically asking how many numbers between 3 and 10, so greater than 3 and less than 10, does 3 divide? And in this case, 3, 6, and 9 are those 3 multiples of 3 that lie within the range of 10. So in this case, it would be 3. But how can I generalize that for any n and d? So basically, any multiple of d can be written in the form of k times d. And this k in my context is my counter. When I plug different values of k, I get different multiples of d. And if I limit that below n, and obviously this will be greater than 0, I can now proceed analytically. Because this is exactly what the question is asking. How many integers that do not exceed n, so that is counting by k, and each time I multiply that k with my divisor, I get a number bigger and bigger, and it wants me to limit that number below n. So I could divide by a d, and then I would get 0 less than k less than or equal to n by d, okay? And you should be able to see that we're trying to maximize k here. We want the maximum integer value for k, and that would be the floor of n by d. And in this case, if I divide 10 by 3 and get a 3 recurring, so it's kind of saying that there are 3.33 integers below 10 that are multiple of 3. But there really cannot be 3.33 integers. And I know for a fact it cannot be 4, right? Because the result is 3 point something. So I'm forced to take a floor of this value, 3.33. And that's what I'm doing here. So you could show this algebra and conclude that this floor is actually the number of integers that fall in the desired range. Okay, so I think that's the content for this video. I'll start next video with a discussion on modular arithmetic with a few applications like hashing functions and pseudo-random numbers, and we'll be looking into the concept of primes. So I'll see you guys in the next one. Until then, you guys have a good day. Bye.